Good afternoon, everyone. I'm Ruiyu. This work is done with John Katz from the University of Maryland, Abhi Shelat from Northeastern University, and my advisor, Huang from Indiana University. Today, my talk about analyzing cut and choose techniques and their use in cryptographic protocols. Let's first look at what is cut and choose. Today is the last day of the conference, and tomorrow I'm going to go camping to a mountain. I'm supposed to bring some matches with me to set a fire. So I get these matches from the hotel. However, I want to make sure that these matches will work tomorrow. What can I do? I will take some of them to test. First one, it works. And I'm not confident yet. I'll take the second one. It works too. And I will like one last chance to try it. It also works. So I can see I'm really confident about these matches. They all works, but the match I need to test, I have to deposit because they are used up. Now I can take the rest of these matches with me to the mountain. I'm really confident that at least one of these matches will work in the mountain. I will not die. But the problem here is, how could I get confident enough with the matches that I won't go die? And how to make sure that at least the rest of the matches will work? This is the idea of cut and choose. What I have just done is a toy example of cut and choose. And here I want to bring up another problem, another point. You can say like test the match here is quite easy and simple. But to take these matches to the mountain may cost energy, cost my luggage space. That means take the match to the mountain will cost more. And this is the idea of cut and choose. It can be applied in many cryptographic protocols, ranging from secure computation, zero-knowledge proof, and some secure delegation of computation. In the rest of my talk, we're going to focus on its application in secure computation to enforce honest behavior. Our mathematical analysis is readily generalizable to other three types of protocols. In the context of secure computation, its matches are garbled circuits. The matchmaker is called the generator. And the testing these matches here is called circuit checking. While taking these matches to the top of the mountain is circuit evaluation, and the custom me is the evaluator. In some cases, I want that at least of these matches work. This is corresponding to SingleCut. A SingleCut protocol will employ some cryptographic treatments such that at least correct circuit in the evaluation where it suffices to ensure security. But sometimes I want to make sure that at least half of the matches here is good. This is corresponding to MajorityCut. A MajorityCut protocol will output the majority of the evaluation result. Thus, it needs the majority of the evaluation circuit to be good to ensure security. And sometimes I will go to a mountain for several times and got a lot of matches here. What I want to do is that make sure that each time I take some of the matches with me, and they all were going to work. This corresponds to batched cut. I'm sorry. Batch cut is the idea to amortize the cost of protocol execution to get a good efficiency, and it's only applicable to batched execution. Despite the difference of handling the evaluation result, all these protocols require the checking of the matches here. They all have to work. In this talk, we are focused on the simplest protocol, SingleCut, to demonstrate our idea on improve the state-of-the-art cut and choose protocol. Existing SingleCut protocol, suggested by Lindon in his paper Crypto 13, advises the circuit evaluator to toss a fair coin for each of the garbled circuit to decide whether to check it or evaluate. It's not hard to verify that S copies here displayed at 5, S copies of garbled circuit will be enough to provide S-bit security. And the expected cost for this strategy is that the sum of checking cost times S over 2 plus the cost of evaluation times S over 2. Previously, researchers have concluded that this is similarly optimal strategy, assuming that the cost of checking and the cost of evaluation are almost the same. But actually, that is not the case. In practical, the gap between checking and evaluation could be very, very large. For example, if you are going to evaluate a circuit, the whole circuit has to be sent by the internet, by the network. But if you are going to check the circuit, instead of sending the gigantic circuit, you just need to send the hash of the circuit and the state of the circuit, a state used to generate the circuit. The bandwidth gap here is application dependent. We take an application circuit of size a megabytes, then the bandwidth cost ratio between evaluating and checking will be 1,000,000 bytes over 48 bytes, which is a factor of more than 2,000. Even we consider the time in terms of running time, the cost ratio is still significant. Our experience shows that this cost ratio could be from 2 to 30 in different network conditions. Based on this observation, our first key intuition is to evaluate less circuit and check more, because checking here is much more cheaper than evaluation. This is very intuitive, and this is indeed the core idea of this work. And the second intuition is to use the probabilistically determined strategy. We let the evaluator decide the probability decides the number of evaluation circuits, and it doesn't declare how many to check or how many to evaluate in advance. This provides us more security, and many previous protocols fail to do so or haven't do it properly. And in the last, we framed the optimization problem into a linear programming to identify the best parameter. I've just given the high-level idea of our work. Now I'm going to give you some more technical details. Our high-level goal is to minimize this expected cost of overall protocol execution subject to the protocol security constraint. For example, the probability of the security failure should be less than epsilon, no matter what kind of strategy the generator plays. Here, we use epsilon to denote the upper bound of the security failure probability, use R to denote the cost ratio between checking and evaluation, and use SGen as eval to denote the generators or the evaluators strategy, respectively. Next, we will instantiate this abstract formulation in the context of SingleCut protocols. We will first explain what is SGen as eval at the start. Then we'll look at how to calculate this expected cost, and finally explain how to instantiate the security constraint. Now let's look at SGen as eval first. Assuming the total number of circuits is a public parameter denoted by n, both the generators and the evaluator strategy can be represented by a random variable over n-bit binary string. Now I'm going to show you how to map in between binary strings and the strategies. To construct n circuits, the generator only needs to decide which circuit to cheat with the bad one. It could just be like, give a good circuit for every 0 bit and give a bad circuit for every 1 bit here. The generator strategy here can be summarized as 0, 1, 0, 0, 0, 1, 1. Similarly, the evaluator only needs to decide which circuit to check and which circuit to evaluate. Thus, the evaluator strategy can also be summarized as 0, 1, 0, 1, 1 here. As we had showed before, this protocol fails only if all the checking passed and all the evaluator circuits are bad. The security failure of SingleCut protocol can be translated as that Sgen equals to Seval. Now we can examine the expected cost of SingleCut. Please note that here, the cost doesn't depend on the generator's strategy. Now assume that I circuits are evaluated and n minus I circuits are checked. Then the cost of evaluating I circuits is I times R, and the cost of checking n minus I circuits is n minus I times 1. And we use xi to denote the probability that exactly I circuits are selected for evaluation. Then the expected overall cost is simply a weighted sum for I ranging from 0 to n. This is the formulation of the expected cost. Recall that xi is used to denote a probability distribution. So all the xi need to be non-negative, and they summing up to 1. Next, we are translating the security constraint. Recall that security fails if and only if Sgen equals to Seval. The ensuring security is equivalent to bounding the probability of this event by epsilon, regardless of the generator strategy Sgen. It's not hard to set this formulation is equivalent to the constraint on the random variable Seval, that any n-bit string won't be picked by the evaluator with probability more than epsilon. Or you can see the probability that the evaluator picks any specific strategy A is bounded by epsilon. This constraint can be further formulated as inequalities of xi, because there are n choose I pure strategies to evaluate I different circuits out of all the n circuits. And each pure strategy can be picked with probability at most epsilon. So therefore, we can conclude that xi should be at most n choose I times epsilon. It turns out this is also enough to ensure security, because if xi is smaller than n choose I times epsilon, then the evaluator could simply pick every pure strategy evaluating I circuits with equal probability. That ensures that none of these pure strategies will be used more often than epsilon. As a recap, we have arrived at a linear program for SingleCut protocols. We could solve this problem with black box calls to standard linear programming solver, but it turns out that this particular linear programming problem can be much more efficiently solved in linear time. The key insight here is that it can be treated as a fractional knapsack problem, where the pure strategies of evaluating I circuits corresponding to the I type of n choose I different objects whose unit cost will be that of evaluating I circuits and check n minus I circuits. And the goal here is to fill up a bag of size of 1 over epsilon units with the minimal cost. A simply greedy algorithm will solve this in linear time. Now the last problem here is to find the best optimal total number of circuits n. Because of the efficient solver, we can do it very practical to do exhaustive search even when the range is very, very large. We further enumerate every possible n within this range to find the minimal one, find the one with the minimal cost. Note that this is sufficient because any n smaller than the lower bound cannot ensure security. But any n larger than the upper bound would perform better than Linto's simple strategy. In fact, this is not good enough. We could optimize the scheme further by dropping the constraint that n, its parameter, is public and fixed in advance. We have addressed this elimination in the following up work available from the given link. And also, we have introduced this idea during the post-session yesterday night. Now we can give a simple comparison of the strategies between the state-of-the-art strategy and our strategy. We measure the cost in terms of bandwidth here, and we use AES as an example. In this case, the cost ratio, bandwidth cost ratio is more than 4,000. In the classical strategy, the weight distributed in several slots. However, in our strategy, the weight most falls is in only one slot. This is an example of using probabilistic strategy improperly. You can see in the classical strategy, they have changed the number of evaluating circuits. But in our strategy, the number of evaluating circuits is almost fixed. But we have a much more total number of circuits. We have more than 2,000, but the classical strategy only has 40. We can see the overall improvements of our technique for SingleCut protocol. Our technique could save from 20% to up to 80% of the overall cost for the cost ratio ranging from 10 to 10,000. And we can find where is the AES in this figure and what is the multiplication of 64 bits floating point number. Our technique can save at least 60% of the bandwidth cost in SingleCut protocols. Similarly, we could also use linear programming to deal with the MajorityCut, because the inequalities is much more complex here. I don't have enough time to explain why this is a formulation. If you are interested, you can see the details in our paper. We can give a simple strategy comparison between the state-of-the-art strategy and our strategy. Here we measure the cost in terms of running time instead of only the bandwidth. We assume that the time cost ratio is a ratio of 10, which is very reasonable based on our experience result. The classical strategy, it uses a fixed number of circuits to evaluate, whereas the total number is 124. But in our case, we use a much more number of much more total number of circuits, and the weight of a strategy falls into several slots, that you can see here. We can see that there's a significant difference between the classical strategy and our strategy. This is the example of the weakness of not using probabilistic strategies. And here we can save almost 1/4 of the running time. For MajorityCut, this is the overall strategy figure. We can save about 1/4 to 90% of the cost for the cost ratio ranging from 10 to 1,000,000. We can also see where is the floating point number multiplication and the AES on this figure. With our technique, we can save about 80% of the bandwidth costs in MajorityCut protocols. The benefit of batched cut protocols are a bit less because, especially for the large batches, it is partly because the batched cut protocols, they are already highly optimized, especially for the large protocols. I have skipped the details for batched cut protocol because they are super complicated and it's hard to explain using 1 or 2 sentences. If you are interested in this kind of protocol, you can search for the details in our paper. And in conclusion, your take-home message is that cut-and-choose protocols, no matter where it's applied, should be appropriately configured based on the security requirement and the cost ratio. The source code for all 3 types of the game server is available on GitHub. Thank you for coming to my talk. I'm ready for taking questions. Thank you.
Are there any questions?
Hi, thanks for your talk. Can you give an intuition about how the SingleCut protocol works without leaking information?
Let me see.
Like normally when something, like the way the majority cut one works is you take the majority of the circuits so that you don't leak information if one of them's right and if one of them fails.
Yeah, in SingleCut, you want to make sure that you don't leak the information. You have some additional cryptographic treatments. For example, if you use the free XOR technique, then if you get two different valid results, then you can get the global data of the circuit. Then you can decode all the circuit and decode the adversary's input, and you don't need the circuit anymore. You can directly compute the output.
If you use the same XOR offset for each circuit.
Yeah, if you use the free XOR technique, you can achieve this very easily. Because if you have two different valid output, you can get the global data or global R for every wire. That means you can decode the whole garbled circuit. The circuit is not a mystery to you anymore. You can see.
So you use the same R for everybody.
Yeah.
Right.
High-level answer is that there's an extra trapdoor, so that if there are two evaluations with different answers, then you use that as a witness to get secrets.
Okay, fair enough. Okay, good.
This is one limitation that you expect.
Right. Okay, good, thanks.
Thank you.
Anybody else? Well, for his talk and for not burning the ballroom down, let's give him a round of applause.
Thank you.